But if you keep using that, I mean, once you define the convolution, you can keep going. You don't have to start the two functions. You actually can define a convolution f, g, and h three function. You can keep going. And this is in 1D now. Go back to 1D. Well, one variable. It depends. So you have a function f, g, and h, and define a convolution between among this. So using three functions, and the idea is you can first define it as convolution between two of them, and then define that is a function. Once you do a convolution between two of them, and then that function, and now do a convolution with the other one, the third one, right? You can define like that, and then write down your definition, and which is fine. And but finally, you see that the final result actually doesn't depend on order. You can interchange all this order FGH or HGF or whatever. The final result will be the same. So the order doesn't matter, but if you first define it, you can like do this two first. I think this is what the textbook do. Yeah, question? No, okay. No, the textbook do the last. It doesn't matter. It's just following the textbook. There's this two first. Right? Because apply the formula, that is square root 2 pi, and then by the definition is f as a function y, and then the convolution g, which is a function also, and then you evaluate at x minus 1, and then dy. Right? So that is just the convolution formula between this function f and then the second function g star h, which is we consider as a single function. Okay, so that's just the formula. Now the next step is to write down the formula for this convolution between g and h. So that becomes another factor of square 2 pi. So all together is like that. So y, and this one, and I can take by all the limit, but that is but the definition is g and the argument like x. I mean, integrate over this argument. I think your textbook called t, and it doesn't have to. I mean, it's a little confusing. This t is not time; it's another variable, and then h, and now this argument is minus dt, and then dy. Okay, and so that you can use, or but another form to use is doing some change of variable. So this is you keep fy, but it changes to the g changes to this argument. Instead of t, you call it z minus 1. And the reason is not obvious, but once you did that, you transform the third one and see what happens. So if t is z minus y, then you just substitute t z minus y here. And becomes the y will cancel, become x minus z. Okay. So this that's this way, the green one. So this is the final definition. If You like a standard form to compare with. And obviously change the integration variable. So we have a y already. Now this dy becomes a we keep the dy. Dtt is c minus y, so dt change to dc. Right. It's g minus y, and then h minus dc dy. Okay, so that's the definition 20.8. So it, I mean it doesn't matter which I mean which line you use. It's just it looks a little bit similar to the one variable or the just between two. So this two is just like you have convolution between f and g and becomes a function of z, and then the the rest is just this convolution with h. So this now the order is just different from where we get to here, right? And the, this formula is slightly different from this one. With both of these two functions have arguments difference between two variables. This is not this is a single variable. This is a difference between three variables. Other than that, that is that doesn't matter. Now the fact that we define like that is independent of the order, you can just like what we did for the original convolution, you can redefine a variable, change a variable, and convince yourself that if you change the variable such that by this standard formula, you're basically interchanging all these position of the C function, uh, so that the position is not important. Another way to do it, or maybe even a little bit easier to understand, is that by defining the convolution, we're saying that the convolution, like going back to F star G, the convolution. The idea is the convolution, if you take the Fourier transform of convolution, it's the product of the Fourier transform of the individual function. This becomes just F times ignoring that all these arguments, so these are spatial, depends on spatial coordinates. Right? And then F and G will depends on wave number. Right? So once we did that, the product of the two Fourier transform obviously doesn't depend on the order because this is just usual multiplication. So the order doesn't matter. You can write that as FG or FG equals GF. And just by comparing this with that, so you know that this is just G star F transform. Right. And compare this with that, you know that the order of the convolution doesn't matter. And likewise, again, now continue like that. And so you have F. Fourier transform. We have three using this definition of convolution of three variables and take the Fourier transform. Obviously, by this generalization, you can group that first and then convolution with the other one, and doesn't matter. The final result will be F. Right now, again, this product is just usual multiplication. It can be rearranged any order. But now there's more possibilities. You can rearrange that like G, F, like that, right? Then obviously that becomes a convolution, a Fourier transform of convolution G, right? That shows that the order of how you put the order in the definition of the convolution doesn't matter, because finally your Fourier transform will always be the same. And, so that's another way to look at that. And it's okay. So and now the formula that we devised. So this, like, if you like to use this one, this is like you know, the the left hand side of equation 20.85 Fy G Z minus Y H X minus Z. So put it like that, and then using this result. So basically, this is saying that the this is a function, right? This is the convolution. And use the inverse Fourier transform formula. So this is a function, and you know the Fourier transform of this object, the convolution, is the product of the Fourier transform of all these three functions. So using the inverse Fourier transform formula, so that is space. I'm going to write on the left hand side. So this is the inverse transform is equal to 1/2 1/2. Right. And the idea is you put the three was F3 Fourier transform F, G, and H. I mean, again, the textbook using omega now. I mean, it's the convention is not consistent in the textbook. That doesn't matter. And the inverse transform here, let's say, x. This is a function x because you integrate over z and y. So the only thing left is x and d omega. Right? And so that is equation 20.85. And now this the only difference between this one and the previous one. Now you multiply 2 pi here, you have 2 pi to the square of 2 pi in the form, the side with the integrating over in the Fourier space. If you compare this 20.85 to what we had before, or just contribution between two functions, that formula doesn't have any effect. That is 20.71. So 20.71 with just two functions. The corresponding formula has no 2 pi factor. But for three functions, now you multiply this to the other side, you see that there's a 2 pi to the 1/2 factor on the Fourier sine. Right? Likewise, if you generalize it to 3D 20.88, then there would be a 2 pi to the 3/2 factor on the Fourier integral side. And those are just coefficient terms. It's okay, so that now this is just like what we did the previous example before. This is a formula. When we write it down like that, you can use this formula. Okay, without redividing that, but just to just now you're using the formula, you just to make sure that you're using the same convention, and remember this factor on the Fourier integral. Okay, and yeah, this is just the inverse transform formula. Yeah, this is the same as equation 20.85. Except that I'm writing it in order. In your textbook, the left hand side is this integral. The right hand side 2 pi times this integral. Otherwise, it's exactly the same. I just ran out of room and have to write on the left hand side. Okay. Right. You look at your textbook, you see that they are the same. It's okay.